Hola, 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 hola. These base functions are called irreducible representations of the same. Okay? These irreducible representations are known as rho lambda, where this lambda is a possible partition of M, where a partition of M is a set of positive integers that sum up to N. Okay? So, for example, the partition will be N, So, therefore, the number of irreducible representations, the number of base functions that we need here is the number of partitions of
¿Hablo por aquí entonces? Vale. Well, the first thing that we need to do is to select a feasible set of base functions or irreducible representations. In our case, we will use the canonical set of irreducible representations, which is the Young orthogonal representation. Okay. So once we have defined all the base functions that we need here, the next step is to compute the Fourier coefficients associated with those base functions using the Fourier transform formula, which is this one right here. Okay. So the main difference here is that unlike the por fuera lo pongo, no sé cómo es. No, por fuera. Venga. Como veis, sin problemas la presentación. Bueno, ¿por dónde iba? So, the main difference here is that unlike in the real domain, the Fourier coefficients are not just numbers. In this case, they are matrices. Okay? So, once we compute all the Fourier coefficients, the last step is to define the functions of the decomposition using this expression right here, which comes from the inverse Fourier transform formula. Okay? So, well, this function f lambda is the function of the decomposition that is associated with the rho lambda irreducible representation. Okay? So, well, with this information, we now have all the necessary knowledge to apply the Fourier transform to the linear ordering problem. Okay? So, if we perform the Fourier transform of the linear ordering problem, we will notice that there are only three Fourier coefficients that are not null, okay, that are not zero. Those are the Fourier coefficients associated with the partitions n, n-1, 1, and n-2, 1, 1, okay? So this means that the linear ordering problem can be decomposed using just three functions, okay? So if we look at these functions, well, we'll see that first we have the fn function, which is just a constant function related to the mean value of the objective function of the LOP. Then we have the fn-1, 1 function, which is related to the first order marginal information of the problem, that is the univariate information of the problem. And well, it can be solved to optimality in polynomial time. That is, it has a p complexity, okay? Finally, we have the fn-2, 1, 1 function, which is related to the higher order marginal information of the problem. And well, unfortunately, it cannot be solved to optimality in polynomial time, so it's NP, okay? So, well, we know that one of the functions of this decomposition has a p complexity, but how can we solve, how can we optimize or solve to optimality this function right here, okay? So, well, in order to do that, we have to take into account that this function fn-1, 1 focuses on the univariate information of the problem. That is, if we consider that the objective function is a probability function, this would mean that this function focuses on statements of this form, okay? So, optimizing or finding the global optimum of fn-1, 1 is totally equivalent to finding a permutation sigma star that maximizes the sum of the objective function values of all the permutations that share at least one position with sigma star, okay? So, well, this expression right here, okay? Well, this problem is just a linear assignment problem with this cost matrix right here, okay? So, well, one could think that computing this cost matrix is really computationally expensive, right? But, well, fortunately, it has been proven that we can compute all the entries of this matrix in just O(n to the power of 4 time using closed form expressions, okay? So therefore, once we compute this cost matrix, the last step is to just apply the Hungarian method or any other method for solving the linear assignment problem to this cost matrix right here. Doing so, we will obtain the global optimum of this linear assignment problem, and therefore we will obtain the global optimum of the Fn-1 component of the Fourier transform, okay? So, well, until now we have seen that the objective function of the low p can be decomposed into the sum of two functions and a constant, okay? A function that has a p complexity, well, that creates an optimization problem with a p complexity, a function with an np complexity, and finally this constant that is related to the mean value, the objective function, okay? So, okay, but are these two functions also LOP functions? That is, given any LOP instance M, that is LOP matrix M, can we decompose that matrix into the sum of two other LOP matrices P and MP in such a way that the objective function of P represents the P component of the Fourier transform and the objective function of MP represents the MP component of the Fourier transform? Well, in order to answer this question, we need to define a linear system of equations, okay? Linear system of equations with two n² unknown variables. n² unknown variables for the entries of the P matrix and n² unknown variables for the entries of the MP matrix, okay? So, well, the linear system of equations that we need to define here is composed of three types of equations. First, equations that are needed to ensure that the sum of P and MP is the original matrix M. Then the equations that are needed to ensure that the P matrix represents the P component of the Fourier transform. And finally, the equations that are needed to ensure that the MP matrix represents the MP component of the Fourier transform, okay? So, well, if we look at the amount of equations that we have here, we will notice that we have more equations than unknown variables. So, obviously, if all these equations are just linearly independent, then the system would be overdetermined and it would be unsolvable, okay? Fortunately, however, we have been able to prove that this linear system of equations has only this amount of linearly independent equations, which is less than 2n², and well, the system therefore is underdetermined, and well, in this case we have proved that it is solvable with infinite solutions, okay? It's important to remark here that all these infinite solutions are totally equivalent from an optimization point of view, and therefore we can select any of them, okay? So, well, once we have obtained the PMP decomposition of a given instance M, the next thing that we can do is to, well, play around a little bit with these P and MP components. So what we can do is to create a set of instances, of modified instances that are based on the P and MP components of the original instance, but with different proportions of the P and MP components, okay? So in order to do that, we will use this expression right here, in which this alpha parameter is a parameter that controls the proportion of the P and MP components, okay? So for example, if alpha is equal to -1, then we have that the output instance, this M apostrophe, is totally equivalent to the NP component of the Fourier transform. While when alpha is equal to 1, then the output instance is totally equivalent to the P component of the Fourier transform. Okay? Obviously, when alpha is equal to 0, this expression right here is just P plus NP, and therefore the output instance is just the original instance that we have decomposed. Okay? So what we can do here is to use this formula to create like a set of modified instances with different values of alpha ranging from -1 to 1. That is, we can create like a transition of instances between the P and NP components of the problem. Okay? So, for example, that's what we have done here. These are two instances from the Lollip library. And well, what these two heat maps show is how the values in the entries of the LOP matrices vary as we vary the value of alpha. That is, as we transition from between the P and NP components of the problem. Okay? So, once we have this set of modified instances, okay, this transition between P and NP, the next thing that we can do is to compare the rankings of solutions of all these instances. Okay? But before doing that, we need to understand what a ranking of solutions or solution ranking is in the context of a combinatorial optimization. Okay? So for example, let's imagine that we have a linear ordering problem of size 3. In this case, the search space is composed of just 6 permutations. Okay? Sigma 1, sigma 2, all the way to sigma 6. And well, obviously here we can use the objective function of the linear ordering problem to assign a certain objective function value to each permutation in the search space. Okay? All these objective function values are just real values. So what we can do is to order all these permutations according to their objective functions values. Okay? So for example, in this case, we have that we have ordered them in a decreasing order as the linear ordering problem is a maximization problem. So in this case, the global optimum of the problem would be sigma 6, that is the solution with the highest objective function value, followed by sigma 2, sigma 4, sigma 1, sigma 5, and finally sigma 3, which is the solution with the lowest objective function value. Okay? So based on this ordering right here, we can create like a ranking of solutions in which the solution with the first rank will be the solution with the highest objective function value, the solution with the second rank, the solution with the second highest objective function value, and so on and so on. And obviously we can generate this ranking of solutions for any given linear ordering problem. Okay? So well, the thing here is that we don't have just one ranking of solutions. That is, because we don't have just one instance. We have like a set of modified instances that transition between P and NP with values from alpha equal to -1 to alpha equal to 1. So we will have, for example, a certain ranking of solutions for the original instance, for that instance M, which is the instance with alpha equal to 0. And then we will have, well, different rankings for all the other instances with different values of alpha. Okay? So what we can do now is to compare all these rankings by computing the similarity or the ranking correlation, well, the correlation between the rankings of all the modified instances and the original instance. Okay? So in order to do that, we have used a measure that is called Kendall's tau B, which is a correlation measure that ranges from -1 to 1, where -1 is a perfect negative correlation and 1 is a perfect positive correlation. Okay? So our idea here is to check how the ranking correlation with respect to the original instance varies as we transition between the P and NP components of the problem. Okay? So taking this into account, the first experimentation that we have carried out here is based on a series of instances extracted from the Lollip library. In particular, we have considered these 7 benchmarks right here. And well, what we have done for each instance is to, well, first decompose the instance into the P and NP components using the Fourier transform. Then we have created this transition between the P and NP components of the problem, creating modified instances with different values of alpha. And finally, for each modified instance, we have computed the ranking correlation method with respect to M, to the original instance, okay? So obviously here we are working with pretty big instances, and obviously we can't compute the ranking of the entire search space in each case. So instead what we are doing here is to estimate these ranking correlations from a subset of random solutions, okay? So taking this into account, these are the results that we have obtained. So here the x-axis represents the value of the alpha parameter, that is this transition between P and NP, okay, where this -1 is NP and 1 is P. And well, this y-axis represents the ranking correlation measure, the Kendall's tau, with respect to the original instance, that is the instance with alpha equal to 0, this one right here. And finally, well, the color of all the lines represent the different benchmarks that we have considered here. Obviously, as you can see, we have aggregated the results for each benchmark in order to compare them, okay? So the first thing that we can see here is that in almost all cases, the ranking correlation between the P component of the problem and the original problem, the original instance, is pretty high in almost all cases. In fact, we obtain values above 0.6, which is, again, pretty high. The only exception here is the SGB benchmark, this red line right here, which is a special case in which the P component of all the instances is just constant, okay? So, well, and the second thing that we can see here is that the ranking correlation decreases pretty smoothly as we approach the P component of the problem, okay? Again, with the only exception of the SGB benchmark. So this should mean that as we increase the value of alpha, instances with similar alphas should have similar rankings of solutions, okay? So based on all these ideas, we have proposed a new meta-heuristic algorithm, a novel local search-based approach that takes advantage of this idea of the PMP decomposition to efficiently solve the linear ordering problem. So the algorithm that we have proposed is called the p-distant algorithm, okay? So given any linear ordering problem instance, the first thing that the p-distant does is to decompose the instance into the P and NP components using the Fourier transform, okay? Once it has done that, the next step is to compute the global optimum of the P component of the problem using the technique that I have explained at the beginning of this presentation, okay? So if we continue using the notation that we have used until now, this P component is the modified problem with alpha equal to 1, okay? So, well, the next thing that the p-distant does is to create a new modified instance with a slightly higher proportion of the NP component, okay? So, this means that it creates a new modified instance with a value of alpha that is slightly lower than 1, okay? So, for example, in this case, we have selected a value of alpha of 0.95, for example. So, as we have seen in the previous experimentation, instances with similar alphas should have similar rankings of solutions, and therefore we expect that, or we hypothesize that these two instances will have similar rankings of solutions, and therefore this global optimum of P will be a good solution for this problem, okay? And therefore it will be a good starting point for a local search procedure, okay? So that's precisely what the p-distant does next. It performs a local search in this instance starting from the global optimum of the P component, okay? Obtaining a new local optimal solution. And well, and now we repeat this process once again. We create a new instance with a slightly higher amount or proportion of the NP component, for example, alpha equal to 0.9, and we perform a new local search in this new instance starting from the local optimum that we have obtained in the previous instance, okay? And well, we continue repeating this process until we reach the original problem that we want to solve, that is, until we reach alpha equal to 0, okay? So, well, the idea of the p-distant is like performing a series of chained local searches in increasingly NP problems, okay? Well, and this variation in the alpha parameter between consecutive instances is just an hyperparameter of our algorithm, okay? That we call the decrement step. So, well, this is the pseudocode of the algorithm that we propose. And well, one thing that you may notice here is that this idea is pretty similar to the other landscape smoothing techniques that are proposed in the literature. In those landscape smoothing techniques, you usually start from a simple landscape, for example, a flat landscape, and you iteratively approach the landscape of the problem that you want to solve. Okay? So in our case, we are doing something very similar, but instead of starting from a flat landscape, we are starting from the P component of the problem, which we can solve to optimality. Okay? So, well, taking all this into account, the last thing that remains here is to check if this p-descent algorithm is really a promising strategy. That is, what we have done now is to check if this p-descent algorithm is better than just performing a series of random local searches, okay, in the original instance. So in order to do that, we have compared the p-descent algorithm with a classical multi-star local search approach, okay? So, well, this experimentation has been carried out on the same 7 benchmark of instances that we have considered in the experimentation about the ranking correlations. So, in the case of the multi-star local search, we have considered 5 executions per instance, and well, in the case of the p-descent, just 1 per instance because it is a deterministic algorithm, okay? Regarding the decrement step of the p-descent, well, we have selected a fixed value of 0.05, okay? Finally, regarding the stopping criterion of the algorithm, well, the p-descent doesn't need one because it's just like a series of chained local searches, a fixed amount of local searches, okay? So in order to have a fair comparison here, what we have done is to, well, for each of the instances, we have performed the p-descent, a run of the p-descent. Well, we have stored the number of local search steps or neighborhood explorations performed by the p-descent algorithm, and we have used that number of local search steps as the budget for the multi-star local search executions, okay? So this way we ensure that for every instance the amount of local search steps performed by both algorithms is always the same, okay? So taking all this into account, the results, the obtained results are summarized here in these box plots. Okay, so each of the box plots represents one different benchmarks. Okay, the y-axis of the box plots represent the relative errors, okay, with respect to the best known solutions in each case. So this means that lower values mean better results, okay? And well, finally, well, this the orange color represents our p-descent and the blue color represents the multi-star local search, okay? So the first thing that we can see here is that our p-descent seems to obtain better results than the multi-star local search method in 5 out of 7 benchmarks, okay? The only 2 exceptions are the SGB and EO benchmarks. As I have explained before, the SGB benchmark is a pretty special case because the P component of the instances is just constant, and therefore it makes sense that our p-descent algorithm doesn't perform well in this case, okay? Regarding the EO benchmark, well, it is a benchmark that is composed of pretty small instances, okay? So it seems that the multi-star local search outperforms the p-descent when the size of the instance is small, okay? So, well, obviously, here we are not taking into account neither the amount of time that the p-descent needs to compute the P and P decomposition, nor the amount of time that the p-descent needs to find the global optimum of the P component, okay? But, well, we have to take into account that these 2 processes only have to be done once per instance, and therefore we think that it is not such an issue from an efficiency point of view. But obviously, this is still a work in progress, so we are still trying to improve this algorithm. So, well, in conclusion, in this work, we have seen that the Fourier transform of the linear ordering problem can be used not only to decompose the objective function, but also to decompose the instance itself, okay? Moreover, we have also seen that working with the decomposed version of the linear ordering problem creates an efficient framework for local search optimization. In fact, in this presentation, I have shown you one example, the p-distant algorithm, but we are also considering other different ideas, such as, for example, using this PMP decomposition to efficiently break plateaus in the linear ordering problem, okay? So obviously there is still much work to be done here, okay? So some research lines that we want to consider in the future include, for example, using this PMP decomposition to create some kind of complexity measure for the LOP, okay? That is using the proportion of the PMP components as some kind of NP hardness measure, okay? And finally, the last thing that we want to do is to try to generalize this idea of the PMP decomposition to other combinatorial optimization problems, such as, for example, the more general quadratic assignment problem, okay? So, well, here you have some interesting references that we have used in this work, and well, that's all. Thank you for listening, and if there is any question, please let me know.
Thank you, Xavi. I have a question to start. For the decrement step,
yes.
When, for example, you choose a really large decrement step,
yes.
The jump of the global optimum is larger, right?
Yes,
so,
yes, that's it. If we select a larger decrement step in general, the global optimum will obtain a worse ranking in the resulting instance, okay?
I think it will be interesting to see if the decrement step will be very small.
Yes.
Then how will the performance change? Like,
yes.
if the global optimum changes just a bit, maybe the local search wouldn't get stuck in a local optimum and just...
Yes, yes, that was our initial guess, but we have seen that there is like a point in which decreasing the value of alpha doesn't make sense, okay? We can decrease it. I have used, for example, a value of a decrement step of 0.00001, and the results are pretty similar to using decrement steps that are a bit higher. So there is like a limit. It's not like we can create intermediate instances in which, after applying a local search, we always obtain the global optimum of the corresponding instance, okay? That's not the case, unfortunately.
Okay, okay, thank you.
Thank you very much, Xabier, for the presentation. I know that it's computationally expensive, but has it sense to take the NP part and decompose it again, obtaining the P and NP part? I mean, some kind of iteration.
Yes. That was one idea that we had at the beginning, but we haven't been able to do so. In fact, we have tried to extend this idea of the PMP decomposition to other problems, for example, as I have said, the quadratic assignment problem, which is a more general case, and we haven't been able to do so. I mean, this idea of the the PMP decomposition is not mine. It's based on a paper from Anne Lorza. Therefore, well, we are still working on it.
Thank you.
Thank you, Xavier. Maybe the question is, it's a bit naive, but would it make sense after several local search steps, so that you have found several solutions, would it make sense to start a kind of a population-based optimization to take advantage of all the solutions that you have found so far?
Well, the idea, the thing is that the idea of the p-distant is not to use it by itself. The idea of the p-distant is to include this algorithm in other state-of-the-art algorithms, such as, for example, memetic algorithms that use strategies as the one that you have mentioned now. So this is just an initial version of the algorithm, and it's just a very basic algorithm because the idea is to include it in or incorporate it in other more complex methods. Okay.
Have you made any experiment to see how the number of global optimas change, or local optima, sorry, change with different values of alpha?
Yes, we have done that. And in fact, we know that as we increase the proportion of the MP component, that is, as we decrease the value of alpha, the amount of local optima generally increases. In fact, well, in a previous work in that I have that, I know that, I think that I presented the last year, well, I don't know. In previous experimentations that we have performed, we have seen that this P component has generally very few local optima. In fact, in many cases, it has just one local optima that is also the global optima, or at least a series of local optima that are like grouped in a plateau, okay, in just one plateau, that is a global optimum plateau, okay. So yes, that's the idea. That's precisely why I have compared our algorithm with the landscape smoothing techniques, because the landscape smoothing techniques are based on this idea about iteratively increasing the number of local optima in the landscape, and our idea is something similar, okay.
So you can, like, say with confidence that increasing the value of alpha makes a problem more complex.
Yes, because, well, I cannot say that with 100% confidence, but yes, we think that yes, because what makes the LOP difficult is not the P part, is the MP part, I mean. And well, we have seen that, for example, the multi-star local search performs better on, let me see, one moment, on these two benchmarks right here. Generally performs better, not our algorithm, but the multi-star local search, okay? And our algorithm too, but well, the multi-star local search performs better in these two cases, which are two cases in which the P component seems to have very high importance, okay? Because the ranking correlation between the P component and the original instance is very high. I mean, there are very similar problems. So in those cases, it seems that the metaheuristic algorithms perform better, okay? But well, obviously, I can't say that with 100% confidence.
Thank you.
But one thing more, and that idea is precisely what what we want to do here about the complexity measure, okay? So using this proportion of the P and P components to, in some way, estimate the complexity of an LOP. Okay? So that's precisely what we are trying to do. But that's work in progress too.
How do you measure the complexity? Just making the sum of all the entries in the instance, or?
No, we still haven't done that. I mean, we haven't created a complexity measure or something like that. But what we have seen is that when a certain benchmark has a higher proportion of the P component, it seems to be a little easier. Well, we can't say this with 100% confidence, but we have performed some experiments and it seems that that's the case, okay? So our idea is to extend this to create a more formal complexity measure, okay, of the LOP. But that's something that we want to do in the future. We still haven't done it.
When you say that it has a more P component, you mean that the instance P has larger values than instance?
Yes, something like that, yes. That's related with the with the proportion of the PNP. That's it. Okay. Yes. In fact, Anne, in the paper that we have considered, well, in this paper, it's in the references, that is this one right here, proposes a way of creating artificial instances with higher or lower proportion of the P and NP components, doing precisely that. It uses an epsilon and just creates a matrix P and matrix NP, and it creates the artificial instance by doing P plus epsilon multiplied by NP, okay? So increasing that epsilon, increasing the magnitude of the values inside the NP matrix, it creates, she creates increasingly NP instances, okay? So that's the idea.
So that's all. Okay, so thank you.